Okay, good morning, everyone. Good afternoon or good evening, depending where you are in the world. Thank you so much for joining us for another great webinar. So my name is Nikola Beshinovic, and today we have an honor to host Krishna Jha from Optym, where he's lead data and optimization specialist, and has been a part of this company since its inception, and still working for well over 20 years now, together with Professor Ravi Ahuja. And today he will tell us more about his ample experience on developing mathematical models and decision-making systems for railways, and particularly focusing on locomotive-related problems, including real-time assignments as well as maintenance. So, and yeah, he will bring us some real-life experiments and implementations. So I would like to give a floor to Krishna. So we'll have about 40 minutes presentation, and then we'll have Q&A. All the questions that you may have along the talk, feel free to put them in the chat, and we'll bring them to Krishna right after presentation. So enjoy, and Krishna, please, you can take over.
Thank you, Nicola, for the introduction. I'm not sure it's going to be a great talk or not, but there's a talk going to be. So there's one correction in the introduction part. As Nicola mentioned, my name is Krishna Jha. I work with Optym, and Optym is a company which is in existence for around 20 years or more than that. And we have been, it was a different name, but became Optym a few years ago. And what we are doing is transportation logistics kind of software for the optimization, data science, or those kind of things. And in that capacity, personally, me have been working in one or other form for the railroads, with the railroads for around 20 years. So I have come across different problems, tried to work on that, very interesting problems. It's very great to see you, some of you here, with whom I collaborated. Dharma is there. We worked together for quite a bit at CSX. So that's my experience. That's the company experience, founded by Ravi Ahuja, as Nicola mentioned. He was professor, and then I was doing PhD with him, and I started when he started company. I started working with him and then solving. So we are trying to solve. Why locomotive?
Sorry, Krishna, can you share the slides, please?
Yeah, I'll do in a second.
Oh, sorry, I'm sorry.
No worries. So why this topic I selected? Because this is the area we have been working. This is the second project we started with Dharma at CSX a long time ago, and then last 2 years I have been spending a lot of time on the locomotive aspects, not only the operation side, but maintenance side. So that brings the thing that let's talk about the spectrum. So that's, we may not go into the details of any of the problem. We'll try to give the scope that what kind of things in locomotive area we're solving. So let me share my screen, and then we'll make a pass through some of the slides I have put together. We may not have to wait until the end for the questions. If you have some questions, so you can ask, feel free to ask that. And I'll try to answer. Let's make it more engaging, and we don't have to cover all slides. Even if we cover some slides, but good way, that will be the good success. Can you see my slide, Nicola?
Yes.
Can you see my screen? Sorry, can you confirm that you can see this?
Yes,
screen?
it's all good.
Okay, good. So let's talk about so why locomotives are important. I believe that some of the participants here are seasoned, they know in and out. Some are probably from academia, some are new. So thought of putting this slide. This is one of the most important assets or aspect of whole railroad operations. there's no science behind it, but I tried to make a conservative estimate saying that considering all the big railroads we have in North America, means US and Canada, and then see how much fleet they have. It may be well above $50 billion of assets they have in terms of locomotives. What they procure, they manage, they operate, they retire, all these things happen. So it's a huge assets, huge set of assets working and then making railroads operate. Generally, again, second estimate that how much operating cost is there on the operating these locomotives in terms of fuel, in terms of maintenance, in terms of all other aspects. It can be easily $20 billion. It can be more also. And then the way I calculated this number, that it's around $80 billion industry here in North America, then around 70%, let's assume their operating ratio. So that brings $56 billion on their expense, and 1/3 can be attributed on the locomotive side. So it's a huge money. So anything we do, the point of having this slide is that anything we do which can make this part better, and the capital they spend in procuring, leasing, or doing those kind of locomotives, or anything, even the operating side, has a huge impact financially. And then qualitative part aspect you go, then there is great benefits on the service quality as well. But there's not one problem to solve. That's what I learned over this last 20 years. There is a set of problems which are all important, all exciting, all interesting, which can be worked on, and then together they can provide great benefits. So if you see in the locomotive area itself, I'm sure there are more problems which can be looked into, but this is something I can define. I can say that these are the optimization problems which is the important for the railroads. And reason of bringing this slide here, I'll spend quite a bit amount of time, that if you are a practitioner, you can see that if some of these problems stick with you, and then should be tackled, you can tackle that. If you are academia and you want to research, I think any of these problems, if you take and then do some good research, that will have great impact on the railroad. So let's look at these problems. And then as time permits, I will take a couple of problems, and then we can do also some case studies, go into more details. So look at these problems. So life cycle planning problem here. Can you see my cursor, Nicola? Can you confirm that also?
Yes.
Okay, good. So life cycle planning problem. This problem you can think of more of a fleet planning. And this is common not only in the railroads, but also in the airlines and different areas, where what you want to determine that how should be my fleet be changing, right? In that term, suppose a railroad has 5,000 locomotives, then in next 10 or 20 years, how many locomotives the companies should be procuring, how many should be leasing, how many should be retiring, and that is governed by a lot of factors. It's a very good, interesting problem where it is governed by a commercial aspect, that how do you see the commercial demands are going to be for the horsepowers, and that demand over the network will determine that what is the power requirement you need to have. But then you have to see in the what kind of fleet you have, what is the age of the fleet, what is the cost of maintaining a locomotive. Right now we have, it is when we should retire, that determine, and then what kind of locomotives you are going to procure, so that you have a balanced, healthy set of fleet which is going to be there. To give an idea, and then don't forget that this also goes to the ups and downs in the market, right? What happens, and then locomotives needs are changing over the time. To give you an idea, a big railroad, for example, might be storing 1,000 locomotives right now, or 2,000. I think 1,000 locomotives might be storing, which is not being used. You can think of 1,000 locomotives being stored. It means they have procured much more than they should have. At the same time, there are other railroads which are running out of locomotives, and they might be running the locomotive, using the locomotives which were procured 50 years, 60 years ago, and then running those locomotives are difficult. So it's a complex problem, and which has a lot of moving parts, and any optimization tool which can bring a good idea, good visibility, is going to be great help. And that has, as I mentioned, that has also applicability on the airline side. So if you come with the good algorithms on to solve this problem for the rail loads, or we can make that problem also available, and then algorithms available for the airline side, because they face the same problem there. On the transportation aspect, there are few problems. I'm sure there are more. So power planning is the problem where you have a scheduled railroads. You have a schedule. You say that I'm going to next 3 months, 6 months. This is the way a schedule is going to be, which may be repetitive schedule. Every week we are running certain trains, and then those trains have some expected horsepower requirements or tonnage requirements. Then based on that, based on the terrain where these trains are moving, you need to come up with the plan that how these trains should be powered. And then when you say how these trains should be powered, at that time you don't look by the locomotive ID. So look at what kind of locomotives types we have, how the fleet is, and then try to define that this train is going to have 2 locomotives of certain kind. For example, or 3 locomotives, 2 from one kind and 1 from other kind. So that is the problem we are trying to solve in power planning. The analogy is in the airlines again. So here they have the flight schedule, which is published 10 months, 12 months in advance. But at that time, they determine that what kind of plane they are going to use for certain flight. So, but they don't give any tail number. They don't say that this is the specific aircraft going to cover certain flight at that time. So that's the interesting part. This is the first problem, at least from Optym side we worked on, and I think we had good results, it was good algorithms. And then this is one. We'll find tens of other publications which happened after also, and they are still trying to solve it and make it better, and bringing some new ideas, new thoughts on how to power planning solve problem should be solved. Then if you know the power plan, then other comes the locomotive assignment, where you go and then make the assignment by ID. So it comes the place where you know that not only that 2 locomotives of certain type needs to be there, but you are also thinking of how to which locomotive should you working, which is the locomotive ID you should be assigning to that. And depending on the context again, whether what kind of rail load it is, it can be solved. They have different time window for which they try to solve this problem. SOP router is the third problem which we worked on, and this is a problem where maintenance and transportation comes in kind of interplay. So you have locomotives, they need to go for certain kind of maintenance for some regulatory requirements, and then you have certain SOPs with certain capacity. The job here is to find that what is the best way you can send a locomotive to the right place at the right time so that it can be maintained. If you don't do it right, then 2 things will happen. One thing will be that a locomotive may become overdue for certain inspection, and then if it becomes overdue, you are losing any productive time on that locomotives. So that's the loss. Other may happen that you can send locomotives too early to a SOP, and then if you do that, then it means you are over maintaining a locomotive, and you are again taking out the productive time that way, because you are doing more. It has to go SOP more over the time, and then you lose the productivity. Third aspect is the SOP side itself, that how we can have a healthy balance of in and out locomotives at the SOP based on the capacity. So that is the area we worked on again, and got some results in that aspect. Locomotive management is you can think of day-to-day operations, where we know, first take a terminal. So Chicago is your terminal, for example. Then you know that how many trains I'm getting in, how many trains I'm getting out, what locomotives they are bringing in, what locomotives do I need to power those trains so that they can go out on time, and then what is happening in the terminal in terms of what locomotives needs to go to maintain, to go to service, or to have some other handling requirements or those kind of things. So this is very interesting problem, very real time. And then if you can do a good job here, yeah, I'll show you a slide where some of the case study in this regard, it can create a big impact in that aspect. And then finally, the trip optimization is where we have not done work, but this is a well-studied area, and you might be aware of some of the software which is being used on the locomotive. So if the locomotive is moving, at that time, how it should be moving, what should be speed and other aspects, so that it can be optimized movements. Fuel is the big cost right now, and then trip optimization can make a big impact on that aspect. Please feel free to stop me if I'm going too slow or too fast. I'll be happy to change the pace so that it can informative for you. But then that's the problem. We have worked for quite some time. My work of area is kind of where we are looking into more closely. I was never aware of so many things are happening on the maintenance aspect. And then as I'm going deeper and deeper aspect, it's amazing that how much optimization can do on the maintenance itself, right? Suppose you have assets and then you spend 10% or 15% whatever money on maintaining those assets. This is huge operations going on. And I got the opportunity to look into that, how this happens in the railroads, how in airlines. It's a big area, I think, where optimization can play a good role. So maintenance, a lot of problems. So this problem, strategic planning, you can think of that. Suppose you have a fleet of few thousand locomotives, and those locomotives require certain inspections over the time, which is sometimes condition-based, sometimes time-based. All right. And then those maintenance requirements, you know that how the maintenance requirements are coming for those locomotives. Then you have shops, and then you know that what shops can do, how the planned work happens, how the unplanned work happens in these shops, what kind of combinations are going on there. Based on that, this optimization problem, or this decision problem you can think of, is to determine that how to pace the work of maintenance, whatever you can plan, so that in the long term, say maybe a few months or a year, the shops are going to have a kind of balanced work. It's not that in November, people are working overtime, they are working 200% time, and then come June, they are working 50% time. How to pace this work so that they can get a balanced work. And if they have more work to be done, then how they can increase the capacity, how they can think and plan for the capacity, so that locomotives can be maintained in the network where there are multiple shops in the right way, right time, and the right pace. That's a very interesting problem, which looks into maybe few months or a year or 2 years in advance. Second problem is modification planning. All right, so this is also an interesting problem. So the railroads spend good amount of time all over the world in upgrading their locomotives and making modifications which are kind of required for the safety or for regulations or for quality of life, whatever it is, but they are going through modifications. And if you have a fleet of certain kind which needs to be modified, then you start thinking that you have a lot of decision here to make. Which locomotives I should be modifying? What should be the time window on which I should be modifying these locomotives? Then when certain locomotives need to modify, how I can combine these modifications with some of the other tasks happening, or some things we know that's going to happen, so that overall in a minimum time frame, all the modifications can happen, so that the locomotives may have to make a minimum number of visits to a shops for the modifications, and the places where the modifications needs to happen, they are not getting overcapacitated, and also the parts which needs to be required, these modifications are supplied on time, so things can happen on time. So this is again interesting problem for that perspective. A lot of moving parts, which brings materials, shop capacity, capital, and then what are the other inspections or tasks going to happen in the locomotives. Heavy maintenance, that's the problem where what you're trying to do, you are trying to plan for a year or 2 years that if a locomotive requires some overhauling or big task which needs to be go to the shop, suppose a locomotive needs to go to a shop for engine overhaul for a week, 2 weeks, maybe a month, or whatever time it takes, then in a year, how should I plan? How should I identify that? That's number one question. Which locomotives I should be planning for the heavy maintenance this year, right? And then once you know these are locomotives I'm going to do the heavy maintenance, when these locomotives should be planned to have those maintenance, where they need to have this kind of maintenance, and how we can make sure that the plan is followed. So lot of what if scenarios, right? We come in picture here that is determined by how much capital you want to spend, what kind of fleet you have, what kind of urgency is there, and then based on that, this problem is a good optimization problem which we tried to solve using MIP, and then found a good result that how this kind of optimization can help in making a right decision for the heavy maintenance. Running maintenance, that's the area also worked on, created some algorithms, and that is unlike heavy maintenance, this is more of a short term. In a week, 2 weeks time, I know that certain locomotives require inspection, certain locomotives have some defects which needs to be addressed, certain locomotives has defects which just identified but may not be urgent but must be taken care of over the time. And then we know that in my network how the trains are running, where the trains are going. We know that which shops have how much capacity, how much workload is there, how much workload they can take. They have certain capacity. And then we try to solve a problem, optimization problem, so that locomotives can reach the shop at the right time, different shops in the network. And they don't have to spend too much time in the shop. So they're out of service for which they are in the shop should be minimum possible. I have a slide if you get a time, but there's more factors you can think of that which determines that how this locomotive should be planned. So once you determine that what are my locomotives going to which shop and when, these two decisions are made from this running maintenance optimization, then these 4 problems comes in the picture you can think of. One is production planning, that we know this locomotive is going to start coming to a certain shop on certain day, or there are locomotives already in the shop and maintenance is happening. Then you start optimizing your slot. You say that, okay, in my shop, I have 20 slots to handle the locomotives where I can do the job. Which slot should go to which locomotive and when? All right, so I am sending a locomotive 1 to certain slot, certain pit for certain amount of time to be repaired or whatever maintenance needs to happen. What is the benefit of doing that? If this is you have limited capacity of in the side of the shop, what you can do, you have limited manpower, what you can achieve, and then limited handling you can do. So certain capability, capacity, all those kind of things. If you properly optimize it, if you do a proper job, it can improve the shop productivity. It means that people are working on the right job at the right time, and then dramatically you can improve the dwell time. So we can make the locomotive available sooner to be used in transportation, which is the revenue making operations in the railroad. So this is important aspect for that, and that you can do for 1 day, 2 days, 1 shift, 2 shifts, 3 shifts, or maybe a couple of days at that point of time. This problem is task planning. Task planning is a commutative optimization problem you can think of. Suppose a locomotive come to your shop and then it has 50 tasks to be performed. Some are must essential, some are not so essential, or some can be postponed. Now, depending on how much criticality is there of that task, and how the locomotive is planned to be used in the plan, you may decide, right? You can choose the combination that in this visit to this shop, we are going to handle these tasks, and then certain tasks will keep it open. And then when the locomotive goes for the next things, suppose it is going for the overall, this task will be taken at that point of time. This, if you can do the good optimization on this area, this is going to reduce the maintenance cost of the locomotives, overall maintenance cost of the system, because you are not trying to send locomotives multiple times to the shop, and at the same time, you know that which tasks go together well, so that you focus on the task which can be done by the same craft or same part, same place, and then not overstretching or stretching the time it spends there. Finally, the craft assignment is the more of the manpower assignments. Now you know that I have so many manpower available in a shift who has certain skill set. Then you know that where the locomotives are and then what needs to be done. You make the optimal assignment that person one should be working on locomotive one on the slot from certain time to certain other time. So that is you optimize your how the manpower used in the shop, so that out of service time is minimum, and then your manpower cost is, they are productive and then do things. And this is the classical materials planning, where you plan the inventory so that you have right parts available in the right shop at the right time to work on the locomotives. So the purpose, I spent a good amount of time on this to give a flavor that whatever you do, there is always a room, there is always interesting problem which you can work on and then make things better. If you have worked on all these problems, then you can work on integrating. You can think of how they have integrated optimization, where you can combine problems and then solve in one go, not the way it is presented on this slide. Let's spend around 10 minutes or so, 10-15 minutes you'll spend on going a bit more details on a couple of problems, and then see what kind of results we achieved. So this is the power planning problem, one of the problems in the previous slide. The inputs, the problem is that are the decisions you are making here. You are saying that which locomotive should have which setup, which trains should have which set of locomotives in the schedule. That's called power plan. So it's the power plan, and then job in the execution is to follow the power plan as much as possible. So for this problem, you get the inputs, what is your rail network, you get all the data, what is your train schedule, which may be repetitive weekly. The problem we solved, it was weekly repeatable, but it can be different time frame also. What is the power requirement? So train tonnage, on the expected train tonnage of the train determines that, and then territory it is going through determines that how much horsepower you need to run a train. Locomotive fleet you have, what kind of locomotives you have, and how many of those available, and then some business rules, a lot of business rules, not some, a lot of business rules in terms of which can connect, which cannot connect, how it should happen, and where you want to restrict, where you want to make it open. All those kind of things goes in input to this model, which consider locomotive ownership cost. Is the objective is that you want to power as many trains as possible with as less locomotives as possible. So that's the locomotive ownership cost. Then you have active pulling, that every time a locomotive is running, and then pulling a train, what is the cost? Deadhead cost is when the locomotives are attached to a train, but it is not actively, it's not on, it's off, in off mode. So here you're trying to reposition the locomotive from one surplus area to another deficit area. So that's the goal. And then light travel is repositioning, but here locomotives move by itself, so it's not attached to train. In that case also, you have to man the locomotive, you have to put a crew specifically to move the locomotive from one place to other place. Constraints are that there should be sufficient pulling capacity to trains. As you say, horsepower, you want to ensure that they have sufficient power, they have sufficient time. There's a constant business rules that how much time should be there for fueling, servicing, all those kind of things. geographical constraints in terms of what kind of locomotives you can use in certain geographical area, or if you have to add, remove locomotives if it is moving on the mountain or those kind of things. That's constraints, and then mostly on the locomotive attributes itself, which says that what kind of locomotive it is and how it can be used for certain kind of trains. So these are the inputs. They are your scope. You can think of objectives and constraints, and this problem is to decide these four things. What should the active locomotive assignment, that which locomotive should be assigned to which train. When I say locomotive, means locomotive type here, that which are locomotive types, how many, which locomotive, and how many should be deadheading. Light travel, what kind of light travel we can make, and then how the locomotive should be connecting from one train to other train. Again, this is not train ID, but by train type itself, you want to say that from train 1, coming from terminal 1, these 3 locomotives should go to certain train. And then this is directly related to one of the aspects which is heavily used in the railroads called consist busting. So they put the locomotives together, and then it is always beneficial to keep them together as much as possible. That reduce the time and effort needed in the yard or terminal, not yard, in the terminal, to handle those locomotives are connecting from one train to other train. So like any other problem, like most of the problem, I'll say, not all the problem, but most of the problem we encounter in railroad, not only locomotive aspect, other aspect, we try to formulate on time space network. All right. And that is the, not only us, but most of researchers, as I know, try to see the problem that way on the time space network and have then different mechanisms. So you read papers, research are happening, but they are trying to have different mechanisms, which are sometimes very different, sometimes very alike also, I'll say. So that's the way it works. I believe that there are more webinars are coming in the near future, where you will be discussing more on some of the solution approaches and techniques for these problems. So here are the train arcs. Train comes, then it goes to the terminals, stations. This is the time. So train comes at the station, then it goes there, and then they are the things that what happened at that station. So if it goes there, and they spend some time being handled, and then they connect to outbound trains and move out from there. So that's the problem in one terminal you can think of. You can start building this, extrapolating for all the terminals, or all the trains, hundreds of terminals, or depending on how the railroad is, and then for all the trains they are running. These are the arcs you can also define, so that which says that whether the locomotives are going from one train to other train. This is kind of train connection aspect we talked to earlier. So train arc, these are the ground arc pulling, and then these are the outbound arcs. So that's very simplistic way. That's the concept on which the formulation is done. So what we did, we created a kind of MIP on that time space network, but we decomposed the problem in 3 parts. Considering the complexity, number of locomotives, number of trains, geography, all those kind of things, it's used to solve in one aspect. So decompose the problem and then kind of solve them sequentially. So it starts with 1 day planning, which means that take the representative set of train schedule, which repeats, say happens every day, what power you need and how powers are coming at the terminals. You solve that problem, take that output, and then some adjustments, scope, then go to the hybrid mode, which is not 1 day, 7 day, but in between here you bring some of the business rules, some business aspects to solve, to take care of that. So we have a lot of objective function factors, if you see in the previous slide. So we bring some of those and then try to solve not on 7 days, but 1 day, and then solve in between 1 day and 7 day, a good set of representatives solve that problem. And then from there it goes to the 7 day, where it's a weekly repeatable schedule. So we expand it, we get these outputs, and then try to solve that, what should be the exact output from that point of view. So MIP decomposed our 3 planning horizon and solve accordingly. If result-wise, if you can see the case I was talking about, had around 500 locomotives in the fleet. These are the daily trains, on average 360 trains departing, 5 types of locomotives, and with those 5 you can have consist types. You can make 11 consist type, and with different combinations. And then there are 74 terminals where the locomotives were connecting from one train to other train. So for this problem, we solved it. You can see the results. It's very impressive results. Number of locomotives required 8% less. Now, if you recall the first slide I was talking, if you solve for all the railroads together, and then if you can reduce the 8% of the fleet, it's a very conservative estimate, $50 billion, 7% of that is a lot of assets, and then related operating cost. So number of locomotives required reduced by 7.5%, productivity improved by 4.8%, deadhead origins, which you compare with the base case, was improved by 2.3%. Assignment consistency, it means that assignment consistency is that you think of, it's good analogy that if you are, say you run every day, and then you have a track you take, and then you run that day. You want to do the same thing every day. It brings easy in the operations execution. Here, if you're providing certain consist to a train, you try to have same consist to that train every day, so that the people who are going to execute, they don't have to worry that Monday it had 3 of certain kind of locomotives, and Tuesday it has different locomotives. They don't have to worry about that. Percentage of locomotive active time, say active time improved by 2.2%, and dwell time reduced by 7.54% or so. So it's a good research, a lot of things, a lot of practical constants. I believe we have papers also, research papers available on this, which we published. And if you're interested, we can go and then learn more about what we did. That was one problem. The second problem, which I can talk a little bit, is the locomotive management. Here, if you recall, you are in day of operation, you are here in 1 day or 2 days, for example, you are in a terminal, and then you see that what locomotives are coming in and what locomotives are required for the output. And you are to optimize for one terminal, and then also they have some network impact also, where you want to bring some network aspect as altogether. So train schedule and ETAs are given to you. For example, you know that which trains are coming, but those trains are not yet there. You know some estimation that when those trains will arrive and what locomotives they are bringing. Once the locomotives are coming, you should also, we have also information that what status that is locomotive of, or whether it requires refueling, servicing, or it is repairing, or whatever there. You know the power plan, that what trains you are going to build, sending out, what are the locomotives those locomotives need, those trains need, and then what are the business roles. You try to optimize that. You want to minimize the departure delay. This is a very common problem. If you are a practitioner for the railroad, this is might be heard. I am hearing a lot that trains are delayed because there are no locomotive to operate that train. That happens a lot. And that's the number one, in my opinion, terminal superintendent role is to see that they have sufficient power to depart the train on time. Maximize locomotive utilization. You want to see that right locomotives should be put on the right train, and they should be dwelling as less as possible. Increase the plan compliance. We talked about the power plan, so you want to ensure that the plan is adhered. Reason we are trying to do that, because power plan is keeping the network in the consideration. Here you're looking at the terminal, so you want to make the have plan compliance. If you don't do that, then some other terminal is going to suffer because of your wrong decision here, or poor decision made at this terminal. Reduce locomotive handling. You want to have minimum number of consist busting or those kind of things, so that locomotives can easily be connected detached from one train, inbound train, and attached to the next outbound train. Constants are the minimum power requirement for the outbound trains. There are some requirements related to how the train configuration should be, what kind of locomotive, what capabilities, and then what locomotive can be in the front, what direction it should be there, all those kind of things. and duration of whatever processes happen at the terminal. So take this, and then your goal is to provide the what locomotives should be attached to what one trains in the planning horizon, which can be a day or maybe less also, maybe more also. So this is again same concept, similar concept, I'll say, not similar, same concept, but similar concept. We formulate the problem on a time space network. If you take a terminal, for example, you see these are the inbound, what are the locomotives or consists coming to that. You can, and these are the outbound power requirements. So you can, these R's represent that you can bring the inbound consist, can assign to the outbound trains. Here are the things you can do, the consist busting. In that case, you can suppose there is one train brings 3 locomotives, other brought 2 locomotives. You can take these five locomotives, you can bust them and then create say 2 new consist where the different set is there for that consist. So you can bust a consist and then you can form a new consist, and this new consist can be assigned to R1 trains. What is there, which is for the balance, we have the sync node, which says that locomotives which remains at the terminal or are still dwelling can be handled there. So we try different approaches. There are a lot of algorithms we worked on, including MIP and some of the things. One which we found is very useful and very practical for the problem we are trying to solve. This is, you can think of more of a real-time solution, is having a construction algorithm and very large scale number research. So this is the technique where this is meta heuristics, very large scale number research, where we try to use some network concept, network flow concept to do the neighborhood search. So in this case, we are trying to move a lot of locomotives, a lot of combinations, but in certain way that we can efficiently identify those and then use that to solve the problem. So if you are interested, there are papers, a lot of papers available, including a survey paper on this meta heuristic, which we find very useful for these kind of problems, and that we adopted for the problem in hand. With that, there are some KPIs. KPIs are kind of, this is the lab environment, you can simulate environment you can think of, not the actual performance, but what we simulate, what we did, we had certain data, right? Certain trains coming, certain train going, what is happening, how the terminal is set up, what locomotives needs to be serviced, or those kind of things. And then have an experienced manager who have around a couple of decades of experience, and then brought the person, say that you create the plan, how the locomotives should connect, and then we did the same thing using the algorithms. So you can think of, if you compare this, almost all the cases, the algorithms did really well. For example, on-time train departures improved, train delay reduced little bits, consist busting happened considerably less. Locomotives were requiring turning happened less. We used locomotives, right, as much not used, but we could power better the train and then made better power plan compliance you can think of. And then something which took half an hour for a person to work, the model can produce that in a couple of seconds, of course. So that's the power we can see, and then which can be used for this problem. The last problem, I'll not talk about this running maintenance, but I will skip this slide and then talk about the production planning, which I mentioned one of the problems, where you want to see that if I have a shop and then I have locomotives which are there already, and then I know that which locomotives are coming in. My plan is to see that how we can assign to different slots and different manpower, so that we can have a good output in terms of the locomotives have to stay less amount of time, and then my slots are utilized, or my people are utilized as efficiently as possible. We tried different experiments on this problem. The reason I'm trying to show the results here, we tried some machine learning or focused approach. And you can see that we try to emphasize different things. For example, here we try to emphasize that what assignments should happen so that my dwell time is minimum, right? And without looking at the graph, if you see here that the current approach, which is a fit approach, what they followed generally by the SOPs, and if you take that approach, and then focused on the dwell and releases, these three things we measured, and there's considerable improvements. By changing the objective, we can see that they can, for the around 2 weeks of data, what you're trying to solve, you can see that a lot of dwell days can be eliminated. It means the locomotives can go out faster in the SOP if they are assigned properly. Other objective, we try to look into the idle time, that how much idle time is there where nothing is happening. Locomotives in the SOP, we can see that we can improve the average idle hours by 12 hours in the SOP. And then release age can be improved by around 7%. So this is the mean time between release, MTBR, that can be improved by 7%. Why it is important? What happens? We have to observe that there are the time in the SOP that things are not being you are doing a lot of things at this. Or you think this analogy is that you work on multiple tasks and at the same time, but a lot of tasks are open and nothing is being released because you're not finishing things and then making the release faster from the SOP or tasks you're completing. Here we are trying to say that if the things are organized, planned, or properly optimized way, you can create a pace, you can maintain a pace and then work on the task in certain way that releases are happening as soon as possible and more efficient way rather than happening at the end of the day or and the shift more and during the shift less. So that's the goal we had here. So that's pretty much I wanted to cover at a high level, and I hope that it helped. It gives some understanding to you what you are working on.
Yeah, thanks so much, Krishna, for this overview presentation and also touching some pretty interesting problems from power planning to production planning. So I have a couple of questions for you already. So maybe to start with the ones on power planning. So one that we got from Warren Powell was on which planning horizon are you focusing? So you mentioned that you do weekly.
Yeah. Right. It was weekly plan. That time we worked on the problem. It was weekly plan worked on.
Okay, and to continue on that one, could you maybe elaborate a bit on linking the weekly plan with the smaller horizon ones, so the hybrid one and the daily one? So is the 7-day one just a combination of multiple daily ones, or is it a MIP model again? So could you say something about it?
Right. So weekly plan is the input, right? So every week, for example, we have a schedule, say 300 trains in that context around that. And then they have a frequency. Some trains runs all day a week, right? Monday, Tuesday, Wednesday, all the way to Sunday. Certain trains work 5 days a week, don't run on Saturday and Sunday. Certain trains run alternate day, Monday, Wednesday, Friday, right? So that's 7 days. That's our goal to solve. So what we did, once we solved in a 1-day problem, we kind of assumed with some approximation that these are the trains running, say, every day, right? So you saw our time horizon becomes 1 day at that point of time.
I'm sorry, I'm still struggling. I apologize. I enjoyed your talk, Krishna. But when you say that you're optimizing over a week, are you actually optimizing over a week? Or are you optimizing day by day over 7 days where each, I mean, literally is a decision, because, you know, trains can take multiple days before they get to their destination. So are you literally have a 7-day problem in your MIP, or are you solve it? Because you talked about the one-day problems. I don't understand how you can solve a one-day problem with railroads.
Yeah, so I think you are right. So one day means you decompose the problem, and then you say that suppose this is what is happening, power in, power out every day, right? So every day, so all the trains are running 7 days, for example. So so those trains.
How do you solve a one day? What is a one day?
Yeah, yeah. What I'm trying to say, suppose these trains are running 2 days after, say 2 days, 3 days or so, right? That trip, the journey ends, but they terminate, for example, at certain place, right? So you can always think of that. What is the termination? Let's take all the terminations, right, happening in the network, and you kind of move to 1 day. So what is representative 1 day, which covers most of the trains which are terminating on that day.
Can I ask the question?
The
May I ask just a simple question? Do you ever feed the MIP 7 days of activities and you optimize over all 7 days? Do you ever solve a 7-day MIP?
Yeah, that's the third stage where you take all 7 days and then solve together.
So you do have a MIP where you optimize over all 7 days. Why would you ever take a MIP and only optimize over 1 day? Because some of those trains will terminate 3 days from now, and you have to think about what locomotives you put on that train now, arriving 3 days from now, because it may impact what you do tomorrow or the next day on a shorter train. I mean, these things all interact.
Yeah, we can do that way. But we have 1 day and 7 days. That's the.
Okay, so in other words, your 7-day, you take departures on the first day that may terminate 2, 3, 4 days out.
3 days, exactly.
Okay, which means if today is Monday and I'm optimizing Monday, I'm not considering. I may need to say, let's say a train requires 2 locomotives, but downstream I need extra locomotives. So do I send the extra locomotives on a train today? So instead of putting on 2 locomotives, I put on 3 or 4. Or possibly I can provide those extra locomotives on a train that departs a day or 2 in the future. So this is where what you do today depends on what you would do
Exactly.
2 or 3 days from now.
Exactly. So once you do the 7 day, you have to consider that. So whether I should put more power today so that I can have more power requirement 3 days from now, where the train is terminating, and then it can power the other train.
I'm not understanding how a 1-day problem could ever work. I'm just confused by that.
Yeah, I think we can have some further discussion on that, and then certainly, yeah, we can.
I'm fine. Thank you.
No worries.
Okay, yeah, and maybe we could do it after the full hour if you are both available. So maybe another question. So it basically comes from Siddhartha Sengupta. So basically, he asks about where do you see the best performance of the algorithms in the planning horizon? Is it on the long term or shorter toward the production? And what about the need to replan certain solutions?
I guess the short term is the direct impact, right? So that is, if you say my opinion, then that is the where if you can make the decision of optimize and work for the short term, it is better place to solve. That's the question. I believe the question is that I believe it is whether I should be solving the more planning side, right, longer term, or should be solving on the short term, right? My experience is that solving the shorter term problem has more impact, more use. You can directly, because in the railroads, unlike airlines, railroads plans are still not followed that much as every other mode of transportation. So short term is.
Yeah, I believe particularly if you are talking 1 year in advance.
Yeah.
Okay, and so staying within short-term or real-time applications, when would you see the need for resolving and adjusting solutions in reality? What kind of events or situations are used now for your algorithms to trigger if you are on that part of management?
So I'm guessing that context is locomotive management, right? Where do the day planning, right? That's the context we are talking here. If that is the context, then what are your variables, inputs? Your inputs are that which trains are coming and their ETAs, right? What is the power requirement on the outbound side? And what is happening in the terminal when the locomotives are released, going to shop or services? If deviations happen on all these aspects, right? If a train is not coming on time, it's now delayed by 4 hours, right? Or if you have a locomotive not coming out of the shop, you thought it's coming out of the shop, then that's the time you have to resolve. But resolve should be fast right enough, right? So that you can take that new input and then solve it fast and give the new output.
Okay,
so
and
deviation in the input, because that's the.
Okay, and now how you have it implemented, does a dispatcher have to rerun it by himself, or he would automatically get a message that the current plan does not hold anymore, and then he should need to replan it? So is there kind of a warnings that would trigger the recomputation?
Yeah, that part still needs to be figured out, right? The way it is designed, that it can be designed the way it is having 3 modes, right? You make some changes by yourself and then say, click on the button optimize. So the way we have designed, it's the optimize button. Planner or manager comes and then say that I want to optimize at this point of time. Click on that button and get the new output. Or make some changes by himself, or make tweaking and then say now optimize again. Click on the optimize button again, and then it will give you the new output.
Okay, and well, changing a topic a bit, there are people in the academia developing algorithms and models, and often aiming to the optimal solutions. So how do you see that working in practice, and what your goal ultimately is, and how do you make the trade-offs between optimal solutions and computation times?
So I think it goes to the assumptions you make, right? So if you're solving in academia, you take the problem, might make some assumptions, right? And then solve that. So what assumptions you are making, that drives that how much compromise you can make. If it is something crucial for the execution, right? And then you can't make that assumption and then solve the problem. That's the big difference. So more and more business rules, more and more of the requirements, if you can handle in your problem, that is the closer you are, better it is. Optimality, 1% gap, 5% gap. Nobody, I don't think anybody cares about that. It's 1% away or 5%.
Since the question related to things going on in the academic community, speaking as the academic, I need to emphasize these are operational problems, and all of these models are look-ahead models. None of these are optimal policies. So you can do a look ahead and find an optimal solution, but that's not an optimal policy. Nothing here is optimal, okay? So even if you, like Google Maps is an optimal solution to a deterministic look ahead, but that is not an optimal policy for solving a dynamic shortest path problem. That distinction has been lost on the academic community for a long, long time. So we can get right down to perfect optimality looking into a deterministic future, but that's just an approximation. It's not an optimal policy. My model looks ahead stochastically, but we approximate. Nothing's optimal.
Yes, and thank you for that remark. And maybe just to put into relation developer as you are and the user, like CSX, for example, how would you convince them that your algorithms should be used? So is it a relative performance toward their current practice, or what would you see as main selling points?
Current practice.
Yes.
That's people can relate easily, right? They can visualize. Otherwise, in the practice, it's the otherwise become theoretical, right? So that okay, seeing the improvement, we don't know how it is going to pan out for our case. So what is happening now? How it can be better, right? That's the comparison. Most of the time we do.
Okay.
Did I answer the question, or question was different? Something?
Yeah, that's good. And just as a follow-up, did you maybe get into a situation that you developed models and expected to have better results, but actually performed not according to the expectations of the practice?
It's hard to say, Nicola.
Okay, maybe we can leave it then for the some other discussion.
I don't know the answer myself.
Okay, well, then just the last one from Warren Powell. So you have this experience of 20 plus years of developing models and being implemented. Could you maybe pinpoint a few railroad companies that are that have implemented your algorithms and that are using today?
I don't know whether you're using or not. I say it's over the time, right? So we worked on the certain problems. CSX was our main partner at that time. On certain problems, we work with them. We are working with other railroad right now on the maintenance aspect. Some are in use, some are in development. So that's the part where things are going on.
Okay. Well, thank you. Looking at the time, I think we had a pretty interesting discussion. There were a few other questions that we didn't have time, but I invite you to reach out to Krishna directly. So with this, I would like to thank everyone joining the session, and also to Krishna. Thank you so much for the interesting presentation. So we plan to continue in a month from now. So we'll share the information about the next talk shortly after this webinar.
Sounds good.